Hey, welcome back to Math with Patrick. Today is July 1st, and we're solving problem number 182 from the Daily Epsilon calendar. Once we finish this problem, we are halfway through the year together. That's crazy. Okay, let's figure out why the answer should be 1 today. We have 21 factorial mod 23, and supposedly this answer is just 1. First, let's talk a little bit about what this mod 23 means. This is from modular arithmetic. Probably the best example of modular arithmetic that you already know is a 12-hour clock. So like once it's maybe 11 a.m., it ticks over to 12 p.m., and then the next hour on the clock isn't going to be 13 p.m., but it's going to be 1. And this idea of cycling back is essentially foundational for modular arithmetic. So, for example, I could say the number 3 mod 6 is congruent to, say, the number 9, because I could cycle the number 9 back to the number 3, and they would essentially be identical in this idea of modular arithmetic. In fact, I would even claim that the number 9 doesn't even exist. I would have to change all number 9s that I see into numbers, or the number 3. Another example, maybe we could have something mod 7. Interestingly here, this is a prime number that might have to do with our problem, or might relate with our problem today in a sec. But if I say something like 2 mod 7, I know a number like 9 again, or maybe the number 16 are both going to be congruent to 2 mod 7. The interesting thing about maybe primes with modular arithmetic is that whenever you have a prime modulus, you're going to be able to get inverses out of all your numbers. A little vocab tip here, an inverse is just a number that brings you back to your identity number. And another vocab word, your identity number, is your do-nothing number. So for example, with multiplication, our do-nothing number is 1. And so a number's inverse is going to be another number that brings you back to the identity number. So with modular arithmetic, basically I'm looking for inverses. And when I'm looking for inverses, I'm just thinking 2 times something is congruent to 1 mod 7. So I guess it should look a little bit more like this. 2a is congruent to 1 mod 7. Maybe I could even say 2 times 2 inverse is congruent to 1 mod 7. I know that if I had an 8 over here, this, I guess, equation or congruency would be true. And so I know that 2 inverse is actually just the number 4. And 4 does exist within this counting system because it is below the 7. And one thing that will be important for our problem today are inverses. I think finding inverses is going to be super important, so we can basically cancel out a lot of the numbers in this 21 factorial. Because, as a reminder, factorials just have you multiply all of the whole numbers down to 1. So when we do 21 factorial, we're doing 21 times 20 times 19 times 18 times 17, all the way down to 2 and then 1. I know that final times 1 doesn't do much, but it's kind of by convention that we have it there. So I'm hoping within the system of mod 23, where we have all the digits from 0 up to 22, I'm hoping that I can find inverse pairs where I pair these up and I get numbers that essentially equal 1 in this system. I know that maybe 24 is congruent to 1 mod 23. And so if I find pairs of numbers that multiply to 24, then I will find numbers and their inverses. So for example, like 1 times 24 maybe could work, but I'm noticing that 24 is kind of outside the realm of mod 23. This 24 would have to be a 1. And then so 1 is its own inverse because 1 times 1 does get me 1. Okay, that didn't really show me much. It wasn't really helpful because I really want to cancel out these pairs. Because say I find like 19 and 17 are inverses, well, multiplying it, I'll get a 1, and then 1s are kind of that identity number, that do-nothing number, and so I can cancel out all those 1s. I could do maybe 2 times 12 to get 24, and both of these are going to be digits that are, or rather numbers that are less than 23, so these cancel out with each other. 3 times 8 is 24. These will cancel out with each other. 4 times 6 will also cancel out. And I think that's about it. So maybe we could keep adding 23 to this number to keep finding other potential like numbers that will help us find inverse pairs. So adding 23, I'll get 47. I think 47's prime. It doesn't really look factorable to me. Might be wrong on that. I'm just going to add another 23 though, because I know I'll get an even number there, and it'll be a little bit easier to deal with factoring an even number. Adding another 23 gets me to 70. So let's try numbers that are that multiply to 70, which is then congruent to just 1 mod 23. The first one that I see is 7 times 10. Although I want to make my search a bit more methodic, let's try starting low and go higher. 70, of course, doesn't exist in the system. 70 is, again, just a 1, so that wasn't that interesting. I could do 2 times 35, although notice, if I take 35 and subtract 23, I'll get 12. So I already have this example. I can't do 3 times anything to get to 70. I've already done the 4. 5. I could do 5. 5 times 14 is equal to 70. And I don't see any of those numbers, 5 nor 14, showing up over here. So I think I found another inverse pair. I don't think I can do 6. I already have it over here, but I can do 7 times 10. All right, cool. So that one gave me 2 more inverse pairs that I could cancel out in my multiplication of this factorial. I just redrew kind of the same thoughts. Here are all the factors from 1 to 21 of 21 factorial. And I found some inverse pairs and I color-coded them and crossed them out here because, once again, when you multiply those inverse pairs, we just get the number 1. Now, the next number to check with our kind of adding 23 idea would be 93. And this is factorable. We could do 3 times 31, though this pair is already right here. We could take 31, subtract 23, and it's the same thing as 8. The next number that we could check would be adding yet another 23. That's 116. But then at this point, these numbers are getting pretty large, and I don't really want to think about the factors of larger and larger numbers. So to get a different strategy, I think I also want to talk about the idea of negative numbers here in modular arithmetic. So let's say I had a lower modulus. I want to say -1 mod 7. Our digits, the numbers, the elements that we're allowed to use are 0 through 6. Those are the only ones that exist in our system. So -1 doesn't exist, and we need to kind of fix it by adding the 7. And so -1 is the same as 6. Importantly, though, we could take numbers that we do have, say maybe 2 mod 23, and we could subtract them and maybe find other representations of this number. So if I subtract a 23 from this, I'm going to get -21 mod 23. And this is just the same as 2. But hear me out. If I try doing the same thing with 12 mod 23, and I subtract a 23 from this, I'm going to get -11 mod 23. And we both know that doing 2 times 12 is going to return us a 1 in this mod 23 system. So it should make sense that -21 times -11 will also do the same. But then it should make sense that +21 and +11 are also going to do the same thing. So let's show that this is actually the case. Let's multiply 21 and 11. These are both numbers that I have within my system. They're both under 23. And doing this multiplication, I think I'll just do something like this. It's a little quick multiplication strategy that I'm just doing with 11s. Adding this up gives me 231. And this is congruent to 1 mod 23, because you can imagine adding up all those 23s would get you to 230. So to me, writing it like this is enough of a proof to be like, yeah, these would all kind of cancel out in mod 23. I'm just left with a 1. So interestingly, using the 2 and the 12 and subtracting and finding some negative values, that strategy was able to help me find new numbers that I could then cancel out. So give me a sec. I'm also going to just kind of go a little bit quickly here on my own and find some more of those negative pairs. Great. So here are the numbers I found. Like, for example, when I was doing the arithmetic myself, I did 23 minus 10 to get 13 instead of the other idea where I did 10 minus 23 to get negative 13. Essentially, either way, I'm finding that 13. So let's just go through these last 5 pairs and see what they cross out. So 21 and 11 are inverse pairs. Then we are going to get 20 and 15. There we go. And I'm pretty sure that this is just going to cross out the whole bunch. 19 and 17 are inverse pairs. 18 and 9. And then 16 and 13. Yeah. I'll just do all the color coding to be precise and, cover all my bases. Great. So all of these numbers have a little buddy. All of these numbers cancel each other out. And we are just left with 1 right here. Cool. So once we do 21 factorial and hit it with mod 23, we just get the number 1. I think there might be something interesting with trying to do like p minus 2 factorial mod p. Maybe there's a proof we could make out there and say that it doesn't matter what prime it is, it's always going to be a 1. Oh, let me say 1 is congruent to. There we go. Maybe that's the case. Maybe it isn't. So I still have some curiosities about this, but we at least solved the problem for today, and I'm all right stopping there. So I'm going to play around with some more primes and see what I can do with that, but I'll finish the video here. Thanks for watching. I'll see you tomorrow. And we're halfway done with the calendar. Woo! All right. Bye.